Hey everyone, I hope you're doing well today. In this video, I'm going to cover partial fraction decomposition. While you may need to decompose improper fractions, this video is going to be focused on decomposing proper fractions. While you can find the timestamps here, they're also linked in the description. In each of these examples, the degree of the numerator will always be less than the degree of the denominators. While in my previous video I went over how to rewrite rational functions in partial fraction form, this video is going to go one step further into solving for each of the constants in the numerators. These are the 4 types of problems I'm going to cover in this video. Let's do some math together. In example 1, we're going to try an example that has distinct linear factors in the denominator. Whenever you see a quadratic in the denominator, you should try to see if you can factor it into 2 binomials. This trinomial is going to factor into x plus 4 times x plus 7. Rewritten, we can say this is going to be 8 over the quantity of x plus 4 times the quantity of x plus 7. Since we have distinct linear factors in our denominator, we can write our partial fractions as a over x plus 4 plus b over x plus 7. Now our goal is to solve for a and b. To solve for a and b, it's always a good idea to get rid of the denominators. To do that, we're going to multiply both sides of the equation by x plus 4 times x plus 7. Between all the denominators, this is the LCD, and it's going to help us get rid of all the fractions. Multiplying this on the left side, these are going to cross cancel, and we're going to be left with just 8. Multiplying it by this partial fraction, the x plus 4s are going to cross cancel, and we're going to be left with a times the quantity of x plus 7. And multiplying it by our second partial fraction, the x plus 7s are going to cross cancel, and we're going to be left with b times the quantity of x plus 4. This equation is going to be much easier to solve now that we don't have any fractions. At this point, it's our goal to either get rid of this term over here, or this term over here. Getting rid of one of these terms will help us solve for either a or b. Let's get rid of this term first. To make this term go away, we need to make x equal to negative 7. If x is equal to negative 7, this entire term is going to get canceled out. We're going to be left with 8 equals b times the quantity of negative 7 plus 4. Negative 7 plus 4 is negative 3, so we'll have 8 is equal to negative 3b. Dividing both sides by negative 3 here, we're going to find that b is equal to negative 8/3. Let's hold on to this for a second. To solve for a, we need to think of a value for x that's going to make this term go to 0. To do this, let's make x equal to negative 4. When x is negative 4, this term becomes 0. The equation we're left with is going to be 8 is equal to a times the quantity of negative 4 plus 7. Negative 4 plus 7 is 3, so we're left with 8 is equal to 3a. Dividing both sides by 3, we find that a is equal to positive 8/3. Now that we have our values of a and b, we can substitute them into our partial fractions. One way you can write your partial fraction decomposition is writing 8/3 over x plus 4 plus negative 8/3 over x plus 7. Cleaning this up a bit, we can write this as 8 over 3 times the quantity of x plus 4 minus 8 over 3 times the quantity of x plus 7. This would be our partial fraction decomposition. Let's try example 2 here. In this example, we're going to have a denominator that has repeated linear factors. The quadratic expression in the denominator factors into 5x plus 2 times 5x plus 2. We can also rewrite this as 5x plus 2 squared. We can rewrite our expression as 20x plus 9 over 5x plus 2 squared. In our decomposed form, we can write this as a over 5x plus 2 plus b over 5x plus 2 squared. Let's get rid of the fractions here by multiplying the entire equation by the LCD. In this case, the LCD, or least common denominator, is going to be 5x plus 2 squared. Multiplying on the left side, these are going to cross cancel, and we're going to be left with 20x plus 9. Multiplying by this partial fraction, this 5x plus 2 is going to cancel with one of these binomials. From here, we're going to be left with a times the quantity of 5x plus 2. And multiplying by this partial fraction, this entire thing is going to cross cancel. We'll just be left with b here. While we can't come up with a value for x to get rid of this b, we can come up with a value for x that eliminates a. Setting this 5x plus 2 equal to 0, we can solve for a value for x that's going to help us eliminate a. 5x is going to be equal to negative 2. Dividing both sides by 5 here, x is going to equal negative 2/5. If we set x equal to negative 2/5, this entire thing is going to become 0. In our equation, we'll be left with 20, which is 20 over 1, times negative 2/5, plus 9 is going to be equal to b. This 5 and 20 can cross cancel and make a 4 and a 1, and we'll be left with negative 8 plus 9 is equal to b. From this, we find out that b is equal to 1. Now that we know that b is equal to 1, we can write our equation as 20x plus 9 is equal to a times 5x plus 2 plus 1. All we did was substitute in 1 for b. Now let's substitute in x equals 0. If we do that, we're going to get 20 times 0 plus 9 is equal to a times 5 times 0 plus 2 plus 1. 20 times 0 is going to be 0, so we're going to be left with 9 is equal to 5 times 0 is going to be 0, so we're going to have 2a plus 1. Subtracting 1 on both sides here, we can say that 2a is going to be equal to 8. Dividing both sides by 2, we can say that a is equal to 4. Now that we have a and b, we can write our partial fraction decomposition as 4 over 5x plus 2 plus 1 over 5x plus 2 squared. This is our final answer. Another way you could have solved this is start off by distributing this a here. In doing so, we're going to get 5ax plus 2a plus b. We can group this as 5a times x plus 2a plus b. To match the left side, these two terms have to be equivalent to each other, and these two terms have to be equal to each other. If that's the case, this 5a has to equal 20, and dividing both sides by 5, we can say that a is equal to 4. Setting these two pieces equal to each other, we can say that 9 is equal to 2a plus b. Since we know a is 4, we can say that 9 is equal to 2 times 4 plus b. 2 times 4 is going to be 8, so we can say 9 is equal to 8 plus b. Subtracting 8 from both sides here, we can find that b is equal to 1. This would be a different way that you could solve for a and b. In example 3, let's practice decomposing a rational expression that has distinct linear and quadratic factors. Let's see if we can factor this cubic polynomial here. When factoring cubic polynomials, I always like starting off by just seeing if I can factor by grouping. Grouping the first two terms here, and grouping the second two terms. For this first group, we can factor out a GCF of x squared, and we're left with x minus 2. And for the second group, we can factor out a GCF of 3, and we're left with x minus 2. Factoring out an x minus 2 from both of these terms, we're left with an x squared plus 3. Now that we factored our denominator, here's our expression. Decompose, we're going to write a over x minus 2 plus bx plus c over x squared plus 3. Since we have a quadratic factor down here, we'll need a linear term up here. Pause and think about what LCD we should multiply this entire equation by to get rid of the denominators. This is what our LCD should be. Multiplying by the left side of our equation, this whole thing's going to cross cancel. On the left side, we'll be left with 5x squared minus 9x plus 19. Multiplying by this partial fraction, the x minus 2's are going to cross cancel, and we're going to be left with a times the quantity of x squared plus 3. And multiplying by this partial fraction, the x squared plus 3's are going to cross cancel, and we're going to be left with bx plus c times the quantity of x minus 2. Distributing here, we're going to get ax squared plus 3a. And distributing over here, we're going to get bx squared minus 2bx plus cx minus 2c. We just distributed this into this, and we FOILed this into this. Now let's rearrange the right side. Let's write these two terms first because they both have an x squared. And we'll follow it up with these two terms since they both have an x. And we'll finish it up with these two terms since they're just constants. Rewriting these two terms using the GCF, we can write a plus b times x squared. Factoring out the GCF here, we can say negative 2b plus c times x. And since there's no GCF for the constants, we can write plus 3a minus 2c. Since these terms right over here with x squared must match, we can write that a plus b must be equal to 5. Since these linear terms must match, we can write that negative 2b plus c is equal to negative 9. And finally, since these constants must match, we can write that 3a minus 2c is equal to 19. Now let's see if we can solve this system. Rewriting this top equation, we can say that b is going to be equal to 5 minus a. Since b is equal to 5 minus a, we can substitute that into the second equation here. In doing so, we're going to get negative 2 times the quantity of 5 minus a plus c is equal to negative 9. Distributing this negative 2 here, we can say that negative 10 plus 2a plus c is equal to negative 9. Adding 10 to both sides, we can say that 2a plus c is going to be equal to positive 1. The reason why we would do this is because now we have two equations that have a and c. So now we can use the equations 3a minus 2c is equal to 19 and 2a plus c is equal to 1. With two variables and two equations, we can solve this like a linear system. To eliminate the c's, I'm going to multiply this bottom equation by 2. Our new equation is going to be 3a minus 2c is equal to 19, and 4a plus 2c is equal to 2. Adding these two equations together, 3a plus 4a is going to equal 7a. Negative 2c plus 2c gets eliminated, and 19 plus 2 is 21. Dividing both sides by 7, we can say that a is equal to 3. Finally, we found one of our letters. Substituting a equals 3 right over here, we can say 5 minus 3 is going to be 2, so we can say b is equal to 2. Now we have our second letter. To solve for c, we can also plug in our a value of 3 right over here. In doing so, we're going to get 3 times 3, which is going to be 9, minus 2c is equal to 19. Subtracting both sides by 9, we're going to get negative 2c is equal to 10, and dividing both sides by negative 2, we'll get c is equal to negative 5. Now that we have a, b, and c, let's substitute them into our partial fractions. Our final decomposition is going to be 3 over x minus 2 plus 2x minus 5 over x squared plus 3. This is our final answer. Here in example 4, we're going to decompose our rational expression that has repeated quadratic factors. Our partial fraction decomposition is going to be in the form of a over x plus bx plus c over x squared plus 1 plus dx plus e over x squared plus 1 squared. To get rid of our fractions, we're going to multiply by the LCD, which is x times x squared plus 1 squared. On the left side of the equation, this whole thing is going to cross cancel with the denominator. We'll be left with x to the 4th power plus 3x to the 3rd power plus 7x minus 1. Multiplied by this partial fraction, these x's are going to cross cancel, and we're going to be left with a times the quantity of x squared plus 1 squared. Multiplied by this partial fraction, this x squared plus 1 is going to cross cancel with one of the binomials of x squared plus 1. Here we'll have the quantity of bx plus c multiplied by x times x squared plus 1. And multiplying by this partial fraction, this whole denominator is going to cross out with this part here, so we're left with x. Here we'll have dx plus e multiplied by x. At this point, it could save you a lot of time if you can find a value for x that gets rid of all the letters except for 1. Looking at these three pieces here, if we say x is equal to 0, a lot of things are going to disappear and simplify things for us. When x is equal to 0, both of these pieces is going to become 0. Over here on the left, all of this becomes 0 as well. When x is equal to 0, all that's left is negative 1 equals a times 0 squared, which is just going to be 0 plus 1 squared. Negative 1 is equal to a times 0 plus 1 is just going to be 1, and 1 squared is just going to be 1, so we're just left with a. Here we just found one of our 5 letters. I'm just going to write that up here. Since a is equal to negative 1, we can substitute in negative 1 for a, and copy the rest down. Let's now try to simplify these three pieces. Here we have negative 1 times x squared plus 1 times x squared plus 1. Foiling this, we're going to get negative 1 times x to the 4th power plus 2x squared plus 1. And distributing this negative 1, we're going to get negative x to the 4th minus 2x squared minus 1. This is our expanded form here. Now let's try expanding this bx plus c times x squared plus 1. Distributing this x, we're going to get bx squared plus cx, and this is going to be multiplied by x squared plus 1. And foiling this out, we're going to get bx to the 4th power plus bx squared plus cx to the 3rd power plus cx. This is as far as we can go here. And here's our last piece. We have the quantity of dx plus e multiplied by x. Distributing the x, we're going to get dx squared plus ex. And that's it for this part. Let's take each of these expanded expressions and put them back into our equation. Now let's rearrange the right side in standard form. For these terms that have x to the 4th power, we can write b minus 1 multiplied by x to the 4th power. For x to the 3rd power, we just have c multiplied by x to the 3rd power. For x to the 2nd power, we have the quantity of b plus d minus 2 times x squared. For the x's, we have c plus e times x, and for a constant term, we just have minus 1. Since our x to the 4th power terms must match, we can write that b minus 1 is equal to 1. Since our x cubed terms must match, we can say that c is equal to 3. For our x terms, we can say that c plus e is equal to 7. And we don't have to worry about these constant terms since they don't have any variables in them. Since b minus 1 is equal to 1, we know that b is equal to 2. There's another letter solved. Here we know that c is equal to 3. And substituting in c equals 3 and down here, we can say that 3 plus e is equal to 7, which means that e must equal 4. Since b is equal to 2, we can substitute that in right here. And we can say that 2 plus d minus 2 is equal to 0. Since 2 minus 2 is going to be 0, we know that d is equal to 0. Finally, we have a, b, c, d, and e. Our final partial fraction decomposition is going to be negative 1 over x plus 2x plus 3 over x squared plus 1 plus 4 over x squared plus 1 squared. And that's our final answer. And that wraps up this video on 4 different examples of partial fraction decomposition. If you found this video helpful, please let me know in the comment section below. Keep up the great work, and I'll see you in the next one.